Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Michelson Interferometer and its applications as the idea of formation of fringes, determination of wavelengths, determination of difference in wavelength and determination of refractive index, and finally the visibility of fringes. Let us begin. Principle by which Michelson interferometer works. The interference is based on the principle of interference of light by division of amplitude. We get interference pattern in two ways, either division in effront or division in amplitude. Here that is based upon division of amplitude is responsible to obtain that interference pattern. Exactly what happened in that particular case, the amplitude of incident beam of light is split off in two equal parts of equal intensity by the process of refraction and partial reflection. And finally, these two split up beams, after travelling unequal optical paths, they are superimposed with each other to form an interference fringes. Let us proceed towards the experimental setup of Michelson interferometer. Here we take a source S. It has an extended source of light from where coherent light is incident. We may use monochromatic source of light or white light. In laboratory, when we perform experiment for monochromatic source of light, we use sodium light, and for white light we use mercury light. Use a slit here. Ray of light passing through that of slit. Use a beam splitter, BS. What is beam splitter? Beam splitter is a partially silvered glass plate. And it has a silver coating just thick enough to split the light coming from that of source S into two halves. Let that two halves, here internal reflection, one ray of light travel, another ray of light travel, it named as light beam 1, named as light beam 2. That beam splitter divides that ray of light, or we can say the light wave, into two halves, light beam 1 and light beam 2. The thickness of that beam splitter is negligibly small, so that beam 1 is transmitted through it and beam 2 gets reflected. That BS is oriented at an angle 45 degree, that is inclined at an angle 45 degree to produce two beams of equal intensity. The intensity of beam 1 and the intensity of beam 2 is same. As we set that beam splitter here 45 degree inclination. Now come to another set of the plane mirror M1 that is fixed. That plane mirror is fixed to receive light after transmission of light from that of beam splitter BS. The reflected beam 1 reaches the mirror M1 and is incident normally on it. That is a compensator C. That light is reflected back towards the beam splitter. That M1, which is the fixed, means it is mounted on a carriage and can be shifted parallel to itself with the help of micrometer screw, which is filled with graduated drum. And a movable mirror M2 that is movable receives light after reflection of light from that of beam splitter BS. The reflected beam 2 reaches the mirror M2 and is incident normally on it. From mirror M2, the light is reflected back towards the beam splitter and gets transmitted through that of beam splitter, and mirror M2 can also be moved with the help of micrometer screw, which is fitted with similarly a graduated drum. And finally, the light wave interfere with each other, and the interference pattern is observed by using a telescope T that focuses at infinity, and set of parallel rays is used to observe the interference pattern. Now come to the topic why we use the compensator C? Look here, the source is extended, we can use either monochromatic source or white light. The purpose of the compensator C is to provide for equal path length in glass for two beams. This equality is not needed for observing the fringes produced by monochromatic source of light, but when we use white light, so equality of path difference is needed. Therefore, we introduce the compensator C. So, compensator is used in case of white light, but in case of monochromatic source of light we do not use compensator. Its work is to equate the path between the light. Next, what be the working procedure? Means what be the exact condition to getting an interference pattern, means the maxima and minima. Proceeds towards working. The shape of interference fringes can be obtained by the mutual inclination of mirror M1 and M2. Say M1 and M2 are mutually inclined. So, they took that a figure, let that one be the optical axis, optic axis, M2, that is the movable mirror. Here is M2. So, the image of M1 is formed that is the image of M1 as M1 dash, and the separation in between M2 and M1 dash, let D be the separation. In between these two as M2, just movement up and down, that distance here is D. That be the position of source S, light beam, that with the angle, that theta. So, here angle of incident is same as the angle of reflection. So, the light wave seems to be come from the source like S2 dash or S1 dash. So, let me prefer what be the path difference in between these two sources of lights, taking the path difference, that light take one is going towards and again reflect back, so that distance will be 2d. If that distance is d, so that distance will be 2d. That be the path difference, this portion be the path difference. Now from that triangle, look here, here is 90 degree, that angle is theta. Cos of theta is equal to cos of this angle, cos of this angle is equal to S1n divided by S2 dash and S1 dash, which is 2d. So path difference is equal to 2d cos theta. In that of triangle we get, so the path difference when M1 and M2 are mutually inclined, at that particular case the path difference delta is equal to 2d cos theta, as we confirm from that figure, which is the path difference in between these two rays which are interfere with each other. That interference is observed with the telescope T. But according to Stokes theorem, that beam 1 suffers a reflection at denser medium and the reflection of beam 2 is at rarer medium. So the additional path difference lambda by 2 is introduced, as the reflection from denser medium, so an additional path difference is introduced. Therefore, actual path difference that is delta dash is equal to delta plus lambda by 2, or delta dash is equal to delta 2d cos theta plus lambda by 2. Now we use the concept for maximum interference and minimum interference. Maxima or minima, constructive interference or destructive interference, or bright fringe or dark fringe, what we named it. For maxima, the path difference is integral multiple of lambda, where n 0, 1, 2, 3 like this. For maximum condition, that is 2d cos theta plus lambda by 2 is equal to n lambda, or 2d cos theta is equal to, that is n lambda minus lambda by 2, or 2d cos theta is equal to, taking LCM and lambda as common, so 2n minus 1 lambda by 2. That is the condition for maxima. Similarly, for minima, the path difference is all multiple of lambda by 2. Similarly, putting the value here, 2d cos theta plus lambda by 2 is equal to 2n plus 1 lambda by 2. We have the relation 2d cos theta is equal to n lambda. That be the condition for minima. By using these conditions for maxima and minima, we observe the interference pattern. So, what be the shapes of that interference pattern? Look here, that is a mirror, two mirrors, means these two mirrors are act as two parallel thin films. Since the distance is d, all over are same, that is filled with air. So, according to the concept of thin film, the interference pattern is observed. So, what be the shapes of these interference patterns? Come to idea of form of fringes. What type of fringes we obtained here? First thing, when d is equal to 0, when d is equal to 0, means the mirror M1 and M2 are symmetrically placed each other. Symmetrically placed to each other. Then the path difference delta dash is equal to 2d cos theta plus lambda by 2. Here d is equal to 0, therefore delta dash is equal to lambda by 2. Hence, path difference is integral multiple of lambda by 2. We obtain the central fringe will be dark. Here the central fringe in the interference pattern will be dark, and the interference pattern is looking like this. Here is the central fringe which is dark, then alternate dark and bright fringes are obtained. Okay. Next condition, when d is equal to lambda by 4 and theta is equal to 0 degree. Theta is equal to 0 degree, that is the angle theta is equal to 0 degree, means mirror M1 and M2 are moved apart, means the mirror M1 and M2 are moved apart. Then path difference delta dash is equal to 2d cos theta plus lambda by 2. In place of d we substitute lambda by 4, or delta dash is equal to 2 lambda by 4, here cos 0 is equal to 1 plus lambda by 2, 2 to cancel out, sorry, that is lambda by 4, lambda by 2 plus lambda by 2, that is lambda. So delta dash is equal to lambda, the path difference, actual path difference, delta dash is equal to lambda. Here as delta dash is equal to lambda, that is integral multiple of lambda, so the central fringe in that of interference pattern will be bright. Here the central fringe in the interference pattern is bright. Here the central one is bright, next dark, in this way the interference pattern we see. Next one, condition number 3, for some angle theta, we have the expression as 2d cos theta is equal to n lambda. Taking the wavelength of light is constant, taking wavelength of light lambda is equal to constant, then what happened, that is 2d cos theta is equal to constant, or cos theta is inversely proportional to that of distance d. Here with the increase of d, the fringes apart to expand radially outward from that of center. From that expression it is clear that with the increase of d, the fringes appear to expand radially outwards from the center. So the fringes are radially outward from that of center. In this way circular fringes are obtained. Next, that be the condition when we take M1 and M2 are mutually inclined, means M1 and M2 are exactly perpendicular. Here the situation is for M1 and M2 are exactly perpendicular. Then we observe that kind of interference pattern. Next, when M1 and M2 are not exactly perpendicular, then the fringes are formed. Three different approaches we take. The approaches like when M1 and M2 are inclined some angle M1 dash. When M1 and M2 are inclined like this, so here that film filled with air, just the thickness is varied, which is known as the wedge shaped film. Another approach, M2, M1 dash. In that of case, we observe the interference pattern just like this. At that of case, we obtain the interference pattern here. We obtain the interference pattern like this. Now, when the source is white light, for white light fringes, taking D as 0, there will be few colored fringes on both sides of central dark fringes we obtained. Let that be the central dark fringe. So, here color fringes are obtained. Different types of color fringes are obtained, as white light is a combination of 7 colors. So, different colors have different wavelengths. For white light, we observe that kind of interference pattern. Now, with the help of that Michelson interferometer, we can easily calculate the wavelength. How we determine the wavelength? Let we take theta as 0. Theta 0 degree means the observer look into the system is 0. The observer look into the system, so that cos 0 degree is equal to 1. We know that two d cos theta, that is cos 0 degree, is equal to n lambda, which implies 2d is equal to n lambda. At that of case, n is the number of fringes appearing or disappearing. At the center. either we take the number of fringes appearing or disappearing at that of center. If that be the interference fringe, so the pattern looking like this, route either appearing or disappearing, that be the number of fringes, the number of fringes disappearing or appearing at the center is taken as n. Which implies wavelength lambda is equal to 2d by n. In this way, by knowing the value of d and n, we can easily evaluate wavelength. Next, determination of wavelength difference. Wavelength difference generally used calculating the difference in various waves of a spectral lines. So, suppose we take a incident light contains two wavelengths. Let the incident light contains two wavelengths, one lambda 1 and another one be lambda 2, so that their difference is very small. So, we obtain set of independent fringes pattern for lambda 1 and lambda 2. Let me take d1, small d, that is the displacement of movable mirror M2 between two successive positions of maximum darkness or maximum brightness. Maximum darkness or maximum brightness. Taking as lambda 1 is greater than lambda 2. If lambda 1 is greater than lambda 2, then small n, that is the orders of center of field, the orders of center of field due to wavelength lambda 1 will be equal to change in n plus 1 order of wavelength lambda 2. Okay, d as we take the distance here between the mirrors, and n1, n as we take number of fringes appearing or disappearing at the center. For lambda 1 let n, for lambda 2 let n plus 1th order. Now what we have, 2d cos 0 degree is equal to n lambda. From that point we get cos 0 is equal to 1. So, n is equal to 2d, that for lambda 1 divided by lambda 1. That equation number 1. Also 2d cos 0 degree is equal to n plus 1 lambda 2. Again here cos 0 is equal to 1, taking n lambda 2 plus lambda 2. So, finally we get n is equal to, from that of equation, n is equal to 2d minus lambda 2 divided by lambda 2. Let equation number 2. From 1 and 2, comparing 1 and 2, here n is equal to 2d by lambda 1, here n is equal to 2d minus lambda 2 by lambda 2. As we say, n order of center of field due to wavelength lambda 1 will be equal to change in n plus 1 order of wavelength lambda 2. Therefore 2d by lambda 1 is equal to 2d by lambda 2 minus lambda 2 by lambda 2 is equal to 1, or taking that equation to this side. So, 2d by lambda 1 minus 2d by lambda 2 is equal to minus 1, or taking LCM, we have 2d lambda 1 minus lambda 2 divided by lambda 1 into lambda 2 is equal to minus 1, or lambda 1 minus lambda 2, that the difference in wavelength, that is lambda 1 lambda 2 divided by 2d. Next, we use the mean wavelength lambda, which is the under root of product of lambda 1 and lambda 2. So, squaring both sides, lambda square is equal to lambda 1 into lambda 2. Now, using that relation here, in place of lambda 1 and lambda 2, we substitute lambda square. Therefore, difference in wavelength lambda 1 minus lambda 2 is equal to lambda square divided by 2d. Let I take del lambda with the change in wavelength or difference in wavelength is equal to lambda square divided by 2d. So, in order to get change in wavelength, we have to know the value of lambda and d. Then putting these values, we can easily calculate change in wavelength del lambda. Now, determining the refractive index by using Michelson Interferometer. Look here, using Michelson Interferometer, we can also determine the refractive index of any liquid. A liquid whose refractive index is to be determined is filled in the empty space in a chamber, which is made specially for that, so that the changes in optical path lengths can be made accurately. That is why we place that liquid in that of chamber. A liquid containing a chamber, if that thickness of that of chamber be small t, which is placed in any arm of that of Michelson interferometer, two arms, where one arm where M1 is placed, another one arm where M2 is placed, any arm we can substitute that chamber which has the thickness small t. In that of same way, when we measure that path difference, let the refractive index which is to be measured is mu. And that refractive index of that material having the thickness t and its thickness small t, then path difference is measured as mu t refractive index into thickness minus t, that is the path difference. Let path difference small d is equal to, taking t as common, so mu minus 1 or d by t is equal to mu minus 1 or mu is equal to d by t plus 1. In this way, to know refractive index when we get the values of d and t. Next, visibility of fringes. What be the condition to visible the fringes in case of Michelson's interferometer? The visibility of fringes and is Vf is defined as, that is the ratio of I max minus I min divided by I max plus I min. Intensity maximum minus intensity minimum, intensity maximum plus intensity minimum. Intensity maximum minus intensity minimum, that is the sum of intensities of the two interfering beams, is also called, that sum is known as the average of a fringe oscillation, which is known as, sum of that one is known as average of fringe oscillation. I max minus I min, that is the amplitude of fringe oscillation. The difference of intensities of two interfering beams is referred as amplitude of fringe oscillation. So visibility of fringes is defined as I max minus I min divided by I max plus I min, or we can say amplitude of fringe oscillation to that of amplitude of average of fringe oscillation. Mathematically we denote the visibility of fringes. That visibility of fringes signifies the contrast of interference in any system, it is signifies the contrast of interference in any system. That fringe visibility, again that fringe visibility is also known as Michelson visibility or interference visibility. Interference visibility, that is Michelson visibility or interference visibility. Let me mathematically calculate I max and I minimum. We know intensity maximum condition, if I1 is the intensity for light wave 1, I2 of intensity of light wave 2, that is 2 I1 I2 cos phi, and phi be the phase difference between the two waves. So, here I1 and I2 are the intensities of two interfering waves and phi and the phase difference between the two waves, I minimum, that be I1 plus I2 minus 2 I1 I2 under root cos phi. Therefore, visibility fringes Vf is equal to, putting this value I max minus I min divided by I max plus I min, we have 2 I1 I2 under root cos phi divided by I1 plus I2. Taking a particular condition, when I1 is equal to I2, means the intensities of two waves are same, that is for coherent waves. Then visibility factor Vf is equal to cos phi, and that cos phi determine the fringe visibility. The fringe visibility is equal to cosine of the phase angle between that two interfering waves, and that cos phi is known as degree of partial coherence. Cos phi is known as degree of partial coherence. Cos phi denotes what be the coherence pattern. When cos phi is equal to 1, condition 1, when cos phi is equal to 1, that is complete coherence. complete coherence. When cos phi is less than 1, that is partial coherence. Condition number 3, when cos phi is greater than 1, then complete incoherence. When cos phi is equal to 0, the maximum value is 1. So cos phi does not greater than 1, therefore cos phi is equal to 0, that is for incomplete coherence. Incomplete coherence. These are the possible scenarios for visibility of fringes. So with the help of this video lecture, you understand Michelson Interferometer, its principle, experimental setup, working procedure. By using Michelson's interferometer, idea of form of fringes, what type of fringes we obtained. When M1 and M2 are exactly perpendicular, these are the possible conditions or possible cases. When M2 and M1 are exactly perpendicular, then these are the interference fringes. And for white light fringe, we take that type of fringes. And again, by using Michelson's interferometer, you can easily calculate the wavelength, difference in wavelength, refractive index, and the condition for visibility of fringes. By defining the visibility of fringes and putting its values, these are the possible conditions for visibility of fringes. So with this useful and informative notes, let me wind up this session. Thank you.